Okay, so hello everyone. Continuing on the previous presentation, mentioning storage and storage slot and name storage slot. Uh, at OpenZeppelin, we just recently introduced namespace storage as a new way to do upgradability, and that's what I'd like to present you. So, storage layouts, we show the easy part just before starting at address 0, but actually it's a bit more complex than that and it's difficult to explore because that's the simple thing. Like when you have your contract, as many of you know, Solidity and Viper start at slot 0 to put the very first value, and then they go on and on with all the values, except if you have an array. Then if you have an array that is arbitrary length, then you hash the slot you're currently in to go to a completely new space, and if you have a mapping, you hash the slot, current slot, with the key or the hash of the key, depending on the length of the key, to again get a completely different location. And this gives us the following grammar. And basically, Solidity and Viper just use root 0, and that's it. And what we can see in this grammar is basically all the slots are accessible because you can just add n. So you can just build a very, very big structure and get to any slot. But at the same time, if n is small enough, then you have an interesting property, which is that if n is small enough and if Keshak is a good hashing function, which we all hope is the case, then each slot should have only one single pass towards the root. That means that hopefully at a given slot we only store one value and there is no conflict possible. And that's interesting and that's important to know because when the storage, like you may not considering that much, like maybe you write your contract, you compile it, you execute it, and you hope that everything works well. Unless you are writing like in Huff, you don't have to worry about that too much. But at some point, maybe you are concerned with like doing upgradable contracts. And if you do upgradable contracts, making sure that you keep the same view of the storage is essential. Because if you go from one contract to another, you upgrade your logic, but you're not reading from the same place, then all of a sudden, like you're not reading your balances correctly, and users don't have their token anymore, and people get mad. So it's important to keep the same storage layout, and it's very easy to go wrong. Like you insert a variable somewhere in your contract, you are shifting your storage. You are resizing a variable, could go wrong. You're reordering the order of your inheritance. That will affect your linearization, that will affect your storage as well. So it's very easy to go wrong, and people have had issues with that. So at OpenZeppelin, we went with the gap approach since version 3, maybe even before in version 4. And the idea with the gap approach is at the end of each contract, we put a small gap being a fixed length array. And what that allows us to do is that even in the future, if we want to add an additional variable in our contract, we reserve some space for that. So we can do a new version that has a new variable declared anywhere, and we reduce the size of the gap. And unless we want to add more like than 50 variables, we're okay. So that somehow resolves like some of the resizing and some of the insertion, if you place them correctly. What that doesn't resolve is the risk that you have if you reorder your contract in your inheritance ordering. So that's why we recently introduced the namespace storage in 5.0. And the thing with the namespace storage, it's a bit more difficult to read. But what you can see is that like this is an ownable contract. There is no owner declared here. We just have a structure that is ownable storage. And on line 30, we have a get ownable storage function that returns a storage pointer. And everywhere where you would normally use a storage value, like in the accessor 973, like the owner accessor, instead of reading from storage like you traditionally do in Solidity, what you get is you get the storage pointer and then you get the value from the storage pointer. And that means that Solidity has absolutely no view on where the storage is, but like we do it manually on line 28, like we say like, hey, the storage is at this location. And the interesting part with that is that if this contract is like part of an inheritance tree and you reorder it, then yeah, it will be placed elsewhere in the linearized contract order, but the storage slot will still be the same. And so it's okay. And that's why we did ERC 7201. And basically 7201 is just this part, so same stuff I showed bigger. It's like, how do we get this ownable storage location? It's not just any random value, it's a value we derived from the fact that, yeah, it's the storage for ownable. And so we have this formula that just says like, yeah, you take like this string, openzeppelin.storage.ownable, you do some fancy stuff with it that I will explain, and you get this value. And then when you have your structure above, we also introduce this natspec comment that say like, yeah, this structure, we are going to put it at this location. That helps with tuning. So like if Solidity wants to focus on Solidity experimental and they don't want to implement that, it's okay, we can do it in user space. I mean, it would be great if the compiler could help us with that, but we don't need a compiler. We can do everything in user space, and that's amazing. And we don't even, yeah, we need assembly, but yeah. Okay, so going back to the grammar, why can we do that? Well, we can do that because technically this is the grammar we have. And we know that if we have a good enough hashing function and a good enough root, like this is going to be a support of the entire space. And the property that this gives us is that if we find any slot that is not covered by the grammar, given a small n, then that can be the root of a new grammar tree that would span over the same storage space, but with no coverage, no conflict at all. So the only thing we need to do is, given that Solidity use L0, we want to get a new value, let's call it this value x, so that Lx and L0 are completely distinct and there is no possible conflict. And that's where this formula comes from. So basically what we do is we take a seed, and the seed is like our initial value, but that could be anything since it's a string. So it could be a storage slot that is used, it could be like the result of some hashing that corresponds to a map. So we cannot use that. But we're going to hash this value. And again, if the previous value can be in the grammar, the hash of the value can still be in the grammar. But if you do -1, then you know you're outside of the grammar, because unless you use n with n being max u into 56, then -1 removes you from the grammar. But still, we cannot use that as a predicate, because someone might use +n with n equal 1, and they come back to the L0 grammar. So once we've removed one, we hash again. And so we take the hash of something that is not in the grammar and know for sure if K-Stack has the right properties, then we are out of the grammar for good. So you could take the deep blue external hash, and that would still be good enough. And you would have your new value. And that's basically what we used to do, in particular with ERC 1967. And that's enough. Like, we have a string, and we get a new grammar, and we are happy. We've got our namespace storages, and we can do upgradable contracts in a safe way. But still, we do something additional. We do this very last operation, and not 0xff. And that's the simple way to do it in assembly. But what that means is that basically says like, hey, take this whole value that is a byte 32, remove the last byte, remove the last two letters or numbers from this hexadecimal string. And that's equivalent to doing something which is between -255 and -0, but you basically go a bit before. And why you do that is because you want to be at the beginning of a bucket. And that's where we go into the ZK EVM world, or not the ZK EVM, but the verkle EVM world, is that we want these new namespaces to be aligned with the verkle buckets. Anybody knows what a verkle bucket is? So if you don't know what a verkle bucket is, I encourage you very strongly to watch this YouTube video that is a replay from Bogota by Guillaume from the ETH Foundation, working on the guest team. And basically the idea is that when we do the verge, we are going to change the way storage is stored on chain. And we're going to do that by not using Patricia Merkle trees, but by using verkle trees. And the verkle trees have this specificity that hashing a path is super expensive. So getting to a random value in your storage space is super expensive, except like if your values are close together, because they are doing something that means that the first 31 bytes of your storage path are going to be like where you are in the tree, and then the last byte is going to be where you are in the bucket. And if you want to access multiple values in the same bucket, it's cheap, but if you want to access multiple buckets, it's super expensive. That's why Solidity mapping will be way less friendly when we go to this world. Like ERC20 will be an issue. And that's also why we say like, hey, in order to prepare for that, we want our namespace storage to be as friendly as possible. In case your namespace storage has values that are consecutive, we want them to be in the same bucket. So that's why we do this 0xff. our main concern at OpenZeppelin with this is that if we do that, it's because we want the code to be cheap. Maybe at some point Solidity and Viper, we want to do that. That would be breaking the storage layout, something that never happened. But if they ever do it, then the -1 won't be enough. The -1 will possibly not be satisfactory if Solidity does the same trick to go like a bit earlier. Then -1 would not be enough. Maybe we would need to do -256, or maybe Solidity, instead of going to the previous bucket, they will go to the next bucket. That way we would be safe. But there is a real subject on where to place storage values in a verkle world. So yeah, that was my talk today. Hopefully you understand a bit better how namespace storage work, how the formula was defined, and maybe you are a bit worried about verkle trees as I am. In that case, let's discuss what to do next with storage layouts.
Thank you so much. Any questions for Hadrien? Yes. Can we get the mic to them, please?
Test? Okay. Yeah. I was wondering about the NatSpec comment that you showed there. Is there any way to automatically...
Let me move next to some speaker so I can hear you. Yes.
Okay, now?
Yes.
Okay, you showed the NatSpec comment. Is there a way to, at the moment, automatically check that the namespace matches, or the computed value that it actually matches with the namespace? Because I could imagine that you're writing multiple contracts, you might just copy over some value, and then in the end it doesn't actually match the namespace, and that way you could get collisions. So is there some like automated testing already, or is this just something for the future?
So no, there is no way to automate that right now. I mean, you could, at some point in the code we showed, there was a constant that was declared. You could replace that constant with just the formula, the mass formula. The risk that you have is that it gets recomputed, because there is a hash, it gets recomputed every time you access it. Again, the fact that we use a const is to go around an issue with Solidity being that some const value are actually like consts that are recomputed every time. So you would have to ask the Solidity team for that.
I think they actually do that now already.
So we'd have to check if it's actually working correctly. We will change the code to reflect that. We were not fully sure because of the hash again. Like we'll check. The Namespace comment is mostly here to help other tooling. In particular, at OpenZeppelin we also develop tooling for Hardhat and for Foundry, and we have tooling that uses this Namespace comment to extract the storage layout of the structure and to make sure that when you do an upgrade, whatever you store at a storage in a namespace storage, whereas the new implementation uses the same namespace in the same way. So that's mostly why the NatSpec is here. Maybe Solidity has the ability to extract storage layout. So maybe Solidity team at some point will help us and say like, hey, if this NatSpec command is here, we're also going to export the storage layout for that structure as part of the metadata. But yeah, I'm not sure if our internal tooling verifies the value. It could do it. It would not be that hard. And we could also just remove the hard-coded X string and put the mass value in the complete value instead. But we'll have to check that the compiler really like stores that as a constant and like processes that before construction.
Thanks.
Anyone else? Yes?
Hello. Yeah. I just want to point out to the upgradable proxy pattern, which is have a slot for the implementation. So the difference here would be like the cleansing part, more or less. So is there a concern that there will be a collision with that, or what's your opinion like in general?
So the the proxy, the contract that I think you mentioned are the 1967 proxies. So this is also an ERC done by the Open Zeppelin contract team. And this is basically the origin of this new ERC. We wanted to store some value at a predictable place that would not conflict with implementation. And this includes the implementation of proxies mostly and other details about the proxy. So this is a continuity because we wanted to generalize that. So this is a much more powerful formula, in particular because we think, basically the 1967 was designed to store just one value. And because we don't do the double hash, like if we store anything more than one slot, there is a risk of collision. So this more complex formula is needed when your namespace starts to grow beyond just one slot. Now the risk of like 1967 should not conflict with grammar L0. And this 7201 should not conflict with grammar L0. Your question is possibly about the conflict between 1967 and this grammar. As far as I know, it's not an issue. But again, like this is the thing that we would want to mathematically formalize a bit more. We tried formalizing them, and it's always difficult because there is this n value that you have to quantify. Basically, depending on the size of your namespaces and your structure, you are statistically reducing or increasing the risk of collision. We don't think it's realistic to have a collision, but mathematically it could happen. So it's difficult to prove and to quantify how unlikely it is.
Okay. If we don't, do we have more questions? That side? No? Okay. Moving on. Thank you so much, Hadrien.